let's say, could that happen differently? Suppose there is a car that's still, and it's beeping. So here comes the sound, and you are running toward it. You're not still anymore. What happens this time, do you suppose?
It's louder as you get closer.
Not louder, but higher frequency, which is higher pitch. Because now you are running in, even though they are being emitted in irregular intervals, you're running into them quicker than they are being emitted. Omitted. So therefore the same thing's going to happen if the source of the sound is still and the observer, or the hearer, is moving toward it. So the same thing, because you're going to run into these quicker, so your ear is going to catch this, and then this, and then this, and then this. And if you're running away from it, the opposite happens. So you can see how these things actually happen. So as you go away, the sound waves are going to be further and further apart because you're running out of them. And so there it goes. Ready for a formula for the Doppler effect? It's not so bad. It takes a little bit of training to use it, but it isn't bad mathematically anyway. Before we do it, I just want to talk about fractions for a second. So we'll start with one that's quite understandable, 1/4. So what happens to the value of this number if I make this go up? What happens to the whole value? So say 1/4 becomes 1/5. Morgan?
It gets smaller.
Right. So if you ate 1/4 of a pizza, you're pretty satisfied. But if it goes up to like 1/10 of a pizza, you might still be hungry. So it's less as the denominator goes up. All right, what happens if this stays the same and this goes up? What happens this time to the value? Hannah?
It gets bigger.
Right, because say 1 goes to 2, you now have 2/4 or 1/2. So as this goes up, the whole value goes up. As this goes up, the whole value goes down. If you've got that, if you understand that, you can do the Doppler effect equation without any problem. All right. So here it is, the frequency, which is what we're looking for here, of the observer. So that's the frequency that is actually heard. So I put the word, some people prefer to think of it, the frequency that you hear is sometimes going to be the true frequency. And that's true when you are still and the sound source are still. We saw that earlier. So the frequency observed, and let's do frequency observed, not observer. Frequency observed or heard can be the same as the true frequency if both are still. But generally, one of the two are going to be moving, at least the problems that I give you. Either you or the sound source are going to be moving, so there's a fraction here. And that fraction is going to operate on the true frequency and either raise it or lower it in this way. So in the numerator, it's velocity of the sound, which has to be given in the problem, or you can go calculate it if they give you the temperature, and plus or minus, which is a little confusing to have in a formula. But it's like if you're going toward it, it's going to go one way, and if you're going away from it, it's going to go the other way. But it won't be difficult. I'll show you how to know whether it's plus or minus. I kind of already did with our 1/4 discussion. The velocity of the observer. So on the numerator, we have velocity of the sound, plus or minus the velocity of the observer. In the bottom, we have the velocity of the sound plus or minus the velocity of the sound source, something that's making the sound. All right, so we got to put that all together into a problem so you can understand how to use it.
Is that times the true?
Yeah, that's times. So you want to put a little dot there. This is times. That is a fraction. And we spend the whole problem coming up with this fraction, and then we just multiply it times the true. frequency, which is given in the problem. So, all right. All right, let's do one. Let's see if you can follow it, and then you try one, and we'll see what time it is by then. This is my last thing that I want to show you, so I'll give you one, and if you get it, then I'll have you do one or two, and that's it for today. All right, let's say that there's a horn that is beeping. The horn sounds, and the frequency of that horn is known. And it's 355 hertz, typical sound frequency. And that's when the car is still. So that's understood. It probably won't always say that. I'll put it in for emphasis since this is our first one. So, got the picture? All right, this car is moving, surprise, surprise. The car's velocity is 21 meters per second toward a still person. And of course, I'm going to ask you, what frequency will the person hear? What will he really hear under this scenario? All right, from our training, let me pause for a minute while you get that down so you can have a clear mind. What do we expect the frequency to do on this? Because the car is moving toward the still person, what do we expect, Molly, for the frequency to go up or down?
Up.
Right. We expect the frequency to go up. So that's very important that before you even pull out the formula, that you know that you know whether it's going up or down. And when the source of the sound is coming toward you, remember the car is moving into its own sound waves and clumping them together, and that's what's reaching you. So the frequency should be going up. So you're expecting this number to be higher than 355 when you finish the problem. So always give me an expectation in your thoughts there. All right, now let's actually do it. Frequency observed, or I'll say heard, which is what we're looking for, equals. All right, let's see if you can help me pick out some numbers from this problem. I'm right here. So Brendan, what's the velocity of the sound?
21.
Actually, that's the car's velocity, and I have to give you the velocity of the sound. So I forgot that. So I tricked you. I didn't mean to. The velocity of sound in the particular temperature of this problem is 345 meters per second. Brendan, what's the velocity of the sound?
345.
Very good, very good. All right, notice that is, I'm plugging in there. It's got to be given. Once in a while, they'll be nasty, and they'll give you the temperature. You have to go calculate the sound with the what's that number, 331.5 and the 0.606, but it's not too bad. So sometimes they'll be nasty, but not yet. All right, now I have a plus or a minus. So I'm going to have to pick one, but I'll do that in a minute. So Brendan, what is the velocity of the observer in this picture?
0.
Right, it's still. The person is still. Would you have said 0 as well? All right, and again, I'm going to fix the plus or minus in a minute. Does it matter whether it's plus or minus? It doesn't, because 345 plus 0 is the same as 345 minus 0. So I don't really have to pick, but I'll pick plus. It won't matter. The bottom's going to count on this one. All right, velocity of the sound again, Brenda?
345.
All right, notice in these problems, this number is the same as this number because the formula says so. Now the plus or minus is going to be very important. And the formula can't tell you which to use, only your mind can. And we'll do that last. And what's the velocity of the sound source, in this case the car? All right, so do we want to add in the denominator to create, remember we're coming up with a fraction here, and we're going to multiply that fraction times the true value, and we're expecting that value to go up. So we want this fraction to have a value that is higher than it was. So we want this value to come up. So do we want this to be a plus number, or do we want this to be a minus number? Only our brain can tell us if we want the whole value to go up. Molly, what are your thoughts?
You subtract it.
Right, very good, because we learned how fractions work. When you're working in the denominator, if you want the whole value to go up, this has to go down. Remember, a fourth of the pizza was a lot more than a tenth. So we want this number to go down so that the whole number comes up. So let's go ahead then. And the true frequency, Brendan, can you find that in the problem?
Frequency